Hello friends, I welcome you in lecture number 4 on singularities and zeros. In this lecture we will talk about zeros of complex functions. So first we define what is meaning of zero of a complex function, and then we will see how to find out zeros of given complex functions. So one simple meaning of zero of a function which we understand as that if we have function f of z, then this point z0 is called a zero of this function if value of function at z0 is 0. This is the meaning of zero which we know from our past experience, that if value of function at some point is 0, say f of z0 equal to 0, then this point z0 is called 0 of this function. Now here we are going to define 0 of order n. So what will be the order of this 0 of a complex function? So for that we consider that suppose a complex function f is analytic at some point z0. So function is analytic at z0, that means there exists a neighborhood of z0 such that function is differentiable at every point in that neighborhood. Okay, as we know the definition of analytic function, that function is analytic at some point z0 if there exists some neighborhood of that point z0 such that function is differentiable at every point in that neighborhood. So because function is analytic at a point z0, function is differentiable at point z0. Now suppose there exists a positive integer n such that value of function at z0 and derivatives of function at z0 up to n minus 1th order, that is f of z0 is 0, first derivative at z0 is 0, second derivative at z0 is 0, and so on, n minus 1th derivative at z0 equal to 0, and nth derivative at z0 is non-zero. If there exists a positive integer n such that nth derivative is non-zero and derivatives of order less than n are 0, then this positive integer n is called order of this 0. z0 is called a 0 of order n of a analytic function f if there exists a positive integer n such that nth derivative at z0 is non-zero and all the derivatives of order less than n are 0, and with value of function at z0 is also 0. So this is the definition of 0 of order n, and 0 of first order is called simple 0. So now using this definition we determine the zeros and order of zeros for following functions. So we start with first function f of z is z minus 1. So first we decide that at which point value of function is 0. So it is clear that function is 0 if z equal to 1. So clearly f of 1 is 0. So 1 is a 0 of this function. Now to decide the order of this 0, we have to first find out first derivative of this function. So derivative of z minus 1 is derivative of z is 1 and derivative of 1 is 0, which is 1. So we are interested in the derivative at z equal to 1. So value of this derivative is 1 at every point z. So therefore at z equal to 1 also it is 1. So here first derivative is non-zero. So therefore we can say that f of z has a 0 of order 1 at z equal to 1, because first derivative at 1 is non-zero and value of function at 1 is 0. Or we can say that z equal to 1 is a 0 of f of z equal to z minus 1, or because it is of order 1, it is a simple 0 of z minus 1. Second function is z minus 4 square. Z minus 4 square. So here also it is obvious that value of function becomes 0 if we take z equal to 4. So clearly f of 4 is 0. So 4 is a 0 of this function. Now to decide the order of this 0, first we find out first derivative. It is 2 times z minus 4 into derivative of z minus 4, which is 1. So it is 2 times z minus 4. So if we find out value of first derivative at z equal to 4, due to z minus 4 it becomes 0. So now we find out second derivative. So second derivative is 2, as it is derivative of z minus 4 is 1. So it is 2. So second derivative at any point z is 2. Therefore second derivative at 4 is also 2. So second derivative is non-zero and first derivative is 0, value of function is 0. So we can say that z equal to 4 is a 0 of order 2, because second derivative is non-zero and value of function at 4 and value of first derivative of function at 4 are 0. So here z equal to 4 is a 0 of second order. So from these two examples, here we have power of z minus 1 is 1. So we have obtained that z equal to 1 is a 0 of order 1. Here we have second power of z minus 4. So and we observe that z equal to 4 is a 0 of second order. So we can generalize this for this type of functions. If we have f of z equal to z minus a raised to n, then this z equal to a will be 0 of order n whenever we have this type of function. So this is just for understanding. Otherwise if you want to prove that order is n, we have to show all these things, but we can quickly decide the order of 0 of a given function if our function is in this form, z minus a raised to n. Third function is cos z into pi by 2. F of z equal to cosine of z into pi by 2. So first we have to decide that value of this function is 0 at which points. So we know that cos z equal to 0 if z equal to odd multiples of pi by 2, that is plus or minus pi by 2, plus or minus 3 pi by 2 and so on. Or we can say that it is 0 if z is 2n plus 1 pi by 2, n belongs to z. So these are the odd multiples of pi by 2. So now instead of z we have z into pi by 2. So this is going to be 0 if we have z into pi by 2 equal to 2n plus 1 pi by 2. So we can see if we simplify this, pi by 2 will cancel out and we have z equal to 2n plus 1 where n belongs to z. So that means plus or minus 1, plus or minus 3, plus or minus 5 all are zeros of this function. So there are infinite number of zeros for this trigonometric cosine function in terms of complex variable. So here first we write that cosine of z pi by 2 equal to 0 if z pi by 2 is nothing but multiple of pi by 2, where n is integer. So this is possible if z equal to 2n plus 1, n is any integer.